So today we are going to start a new lecture on signals and systems. And in this particular lecture, we will observe the signals and systems from a different perspective. And that perspective is basically the perspective of vector space representation. So today, let me start the topic of today's presentation, that is the vector space representation. Vector space representation of signals. And gradually we will understand that how this vector space representation will help us in representing the signal from a different perspective, from a different paradigm altogether. So as you know, in order to represent the signal as a vector, so we have to consider dimension of the vector. And to start with, let us consider that the dimension of the vector being 2. So let us assume that the dimension of the vector being 2. So let us assume that n, that is the dimension of the vector, is equal to 2, so that we can understand the concept, and gradually we can also extend this dimension to a higher one altogether. And during this particular representation, this vector space representation of signals, we'll start our discussion with a discrete time signal, and gradually we will extend this analysis to the continuous time as well. So for example, suppose I am having one signal with a dimension of 2, I mean a particular signal which has been represented in the vector space form and with a dimension of 2. So how can I represent this signal? Suppose the signal what I want to represent is given by, say, let it be x. That is the signal. So that can be represented if the signal is a two-dimensional signal. So I can represent the signal as simple as like this. Say, let it be x of 1 and x of 2. That is the simplest representation of the signal in the vector space form. And remember, these two components, this x1 and x2, they are independent to each other. That means x1 is having no relation with x2 and vice versa. So we have one signal. This signal is represented by x, and that x is having two components because it's a two-dimensional signal. And in the vector space notation, I can represent the signal as x1, x2. Now if I assume, okay, the signal is having a dimension of 10. So let us extend this to a dimension of 10. Another signal, let the signal be y. So I can now represent the same signal as, say, y1, y2, y3, so on up to y of 10. So here we have altogether 10 different components, and these components are freely choosable components. That means one component has nothing to do with the other components. So y1 is completely independent to y2, y2 is completely independent to y3, and y3 is completely independent to y4, y1, so on and so forth. Now, whenever we represent any signal in the form of a vector like x1, x2, or y1, y2, y3, y4, and so on, so we have to understand what is the basis function of this kind of vector space representation. So what do you mean by the basis function? So basis function is something, or basis signal is something by virtue of which we can construct any signal or any vector in that particular vector space. So the basis of any vector space represents a set of functions through which we can represent any signal, any vector in this particular space. For example, we all of us know, say, the complex number, for example, right? Say, let us consider one complex number. So one complex number is represented by, say, c is equal to say a plus ib, or let it be something like that. Say c is equal to ai plus bj in this particular form. So I is basically the unit vector in one particular dimension, and j is the unit vector of another dimension. So for this particular vector ai plus bj in this particular form, I can find out the corresponding basis functions as I comma 0 and 0 comma j. So from that we can simply extract. So if the representation is something like that, ai plus bj, so I comma 0, this is one particular basis function, and the second basis function can be represented as 0 comma j. So what do we mean by that? So if I have these two functions like I comma 0 and 0 comma j, by virtue of which what we can do, we can represent any signal or any function in this particular vector space. So how can I get this c is equal to a I plus bj in this particular form? So that is quite simple. So if I consider this as my basis function, suppose if I call it like say b1, and suppose it's the second basis function if I call it say b2, so this particular c can be represented as a times b1 plus b times b2. So similarly, any function, any vector which is represented in this particular form ai plus bj, so that can be represented, or that can be finally visualized in this particular notation, a into b1 plus b into b2, where a and b, these are the corresponding weights, and b1 and b2, they are the corresponding basis functions over there. Now coming back to our discussion, what we are saying, suppose I am having one particular vector which is having a dimension of 2, and that particular vector x is represented by x1 comma x2. That's all right altogether as of now. Now let us now extend this one. Let us now extend this one to a dimension 5. Suppose the dimension of the vector is 5. Suppose this is my vector x, the signal is x. This can be represented as x1, x2, x3, x4, x5. So far so good. Now the thing is that I have to understand what is the basis function. So from that I have to extract. Now as of now, let us assume that this x1, x2, x3, x4, x5, these numbers are simply real numbers. So they can assume any value from minus to plus infinity, the real numbers, not the complex ones. So now if I just observe this representation, the signal x is represented by x1, x2, x3, x4, x5. Already you are quite acquainted with what is known as the sequence. So this is basically a sequence. This x is represented as a signal x is represented as a sequence whose dimension is given by 5. We have 5 different variables or 5 different components like x1, x2, x3, x4, and x5, which are independent with each other. Now with this representation, now I have to understand what should be a basis function. That means I have to extract the basis functions through which I can really reconstruct. If I know these basis functions, through which by multiplying these basis functions, individual basis functions with the corresponding weights, I can really extract, or I can really formulate the signal x itself. So what are those basis functions? Now here the dimension is 5. Now since the dimension is 5, so I can have, previously I have shown you, for this particular complex number ai plus bj, we have a two-dimensional thing. So accordingly, we have two different basis functions like I comma 0 and 0 comma j. Now here we have a dimension of 5. So accordingly, I can have 5 different basis functions. So what are those 5 different basis functions? So I can simply write these basis functions, say, and these basis functions are known as the orthogonal basis functions. So this b1, the first one is given by 1, 0, 0, 0, 0. The second basis function b2 can be represented as 0, 1, 0, 0, 0. The third basis function b3 can be represented as 0, 0, 1, 0, 0. The fourth one, b4, can be represented as 0, 0, 0, then 1, then 0. And the fifth one, b5, is represented as 0, 0, 0, 0, 1. So I have completed formulating the basis function b1, b2, b3, b4, b5. Now any signal, say for example, I am having over this particular signal x, which is given by x1, x2, x3, x4, x5. So now once I know the basis functions, which are the basic components to ultimately reconstruct the signal. So once I get this basis function, now I can represent the signal, this particular signal x can be represented as a summation, weighted summation of this basis function. So this is basically x1 times b1 plus x2 times b2 plus x3 times b3 plus x4 times b4 plus x5 times b5. So as simple as that. So once I know the basis function, then it is very easy, pretty easy for us to reconstruct the signal, any signal on this particular vector space. Now in this particular lecture, what we are trying to emphasize is that we are trying to visualize the signal. We are trying to visualize the signal in the vector space representation, in the vector space form. And once I complete this lecture, then you can understand what is the importance or what is the utility of observing the signal from this different mathematical perspective. Now once we are quite familiar with this vector space representation, now instead of taking only one basis function, or rather only one signal over there, now let us consider two different signal over there. Say let us consider two different vectors are there. One vector is represented by say x1, which can be represented as say x11. So for the simplicity, I'm just using a two-dimensional signal x11, x12, and the second one x2 is given by x21, x22, right? So x1 is one vector, a signal, a sequence, which is having two components, two-dimensional signal x11, x12. X2 is another vector which is having two components, x21 and x22. And remember that these different variables, they are completely independent with each other. Now we are in a position, sometimes we are interested in finding out the inner product. You are very much familiar because already have studied in the vector algebra what is meant by the inner product or what is meant by the dot product and all these things. Now sometimes we are very much interested in finding out the inner product between these two vectors. Basically here these are the signals. So the inner product, loosely it is also called dot product. So inner product between these two vectors, typically it is represented in this particular form, x1 comma x2, and that is basically given by x1 on. So you have to understand the corresponding weights, x11, x21 plus x12, x22. Now if you have a multi-dimensional, more than two-dimensional signal, say for example 5-dimensional signal, 10-dimensional signal, or even more higher dimensional signals, so in that case you can simply find out the inner product between these two vectors. Remember, while calculating the inner product, you have to ensure that the two different vectors between which you are finding out the inner product, these two vectors must be having the same dimension. So I cannot find out the inner product of a vector whose dimension is 5 with another vector whose dimension is 10. This is never possible. The thing is that you have to find out the inner product or dot product between two vectors having the equal dimension, x11, x12 over here for the first vector and x21, x22 for the second vector. So x11, x21 plus x22, x12, x2. Now, as of now, in our discussion, we have assumed that these numbers, these individual numbers like x11, x12, x21, x22, these numbers are basically the real numbers. So they can assume any value from the set minus to plus infinity. Now, before moving further, let me tell you another thing. So whenever you are trying to find out the inner product between the two vectors, and these two vectors are identical vectors. So for example, the inner product between two vectors which are identical, unique or identical. That means what? I'd like to find out the inner product between x1 with x1 itself, x1 with x1 itself. So that gives rise to what? x11, x11 plus x12, x12. That means what? x11 square plus x12 square. Now, as long as this x11, x12, these are the real numbers, it doesn't create any problem. So real number square is always a real number, and and obviously positive real number over there. And if this both x11 and x12 they are 0, that means a 0 vector. In that case, the inner product between these two vectors will be 0 itself. Now the problem is that the catch is that let us assume that these x11, x12, these numbers are not the real numbers, rather they are the complex numbers. So they have the corresponding imaginary component inbuilt with them. So in that case, I cannot write x1. So even if I write like, even if I find out the inner product or dot product between two identical vectors, so in that case, now if you just simply find out the x11 square, and if you have the I term over there, the imaginary component over there, then this I square will give you something that is negative. And that is not at all something which you expect from the inner product, because ultimately this inner product will give you the squared magnitude of that particular vector. So what is that? This x11, x12, these are the two components, and if I have like x11 square plus x12 square, that will give you the squared magnitude. For example, I am having this vector, say for example, c is equal to ai plus bj in this particular form. What is if I ask you what is the magnitude of this particular number? C is equal to ai plus bj. So you know that is basically square root of a square plus b square, as simple as that. Now, if I consider that, okay, this ai, this is itself your x11, bj, this is itself your x12, and if you just find out ai whole square plus bj whole square, that will give you something negative. So obviously, the inner product between two vectors which are unique, and that will basically give you the squared magnitude of that particular thing. And that squared magnitude cannot be negative, but it can be negative when these numbers are, these x11, x12, these numbers are imaginary in nature. So therefore, we have to do a slight modification in our representation of the inner product. So what is that modification that we are looking for? So the modification in the definition of inner product, otherwise the meaning of the inner product will become invalid. So the modification takes place in this particular form. Say x1 comma x1, I would like to find out the inner product between these two. So this is basically, I cannot write simply like x1 comma x1, rather I have to write like x1 comma x1 bar. That is the complex conjugate. So now if the elements are real in nature, x11 and x12, if they are real in nature, then making them complex conjugate will not make any change. But if not, in that case, obviously, the numbers will be different. So for example, say x1 is given by x11, x12, as I mentioned already. And now try to understand that this x1 this x1 on this particular thing is not a real number. This x1 2, this is not a real number. These numbers are basically the complex. I mean, you have the imaginary component in that. So in that case, if you would like to find out the inner product, so what about this x1 bar? This x1 bar is given by x11 star, that is the complex conjugate over there, and x12 star, that is the complex conjugate over there. So now if you would like to find out the inner product between the two same vectors, so that will give you what? That will give you x11 star plus x12 star, which is basically mod x11 square plus mod x12 square. And this particular thing, this mod x11 square plus mod x12 square, this particular thing can never be negative. It is always positive, and in case when both of them x11 and x12 they are 0, in that case only that will become 0. So for a 0 vector, this will be 0, and for a non-zero vector, even if it is having some imaginary component within that, so that will be positive itself. So that modification I have to take into account to ensure that the inner product between two vectors, two identical vectors, cannot be imaginary or negative in any sense. Similarly, if you have like the inner product between any two vectors, any arbitrary vectors, not like x1 with x1. So I'd like to find out the inner product between x1 and x2. So that is given by x1, x2 bar, which is basically, in general, I can write like x11, x21 star plus x12, x22 star. So that is all about the vector space representation of the signals, and accordingly we have to represent the signal, the inner product, in this particular form. Now the thing is that now while I have started today's discussion, so I have told you that today we will observe the signals and systems from different perspective. Now over the last 15 minutes or so, you might feel that this entire thing is too much oriented towards mathematics, and it is having no significance with the signals, with the notion of signals and systems that you have already studied. So for that, I would like to refer back to this particular slide, where we have got like a 5-dimensional vector represented by x1, x2, x3, x4, x5, and we have observed the 5 different basis functions b1, b2, b3, b4, b5. So just by observing this basis function, can you find out anything? Can you relate anything? Do you have any significance with any of the signals that you have studied before? Basically, what is happening? I'm having the signal, say b1, that is a basis function, the first basis function, b2, that is the second basis function, b3, the third basis functions, and so on and so forth. So these are basically what? 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0 0 0 0 1. Basically, these are nothing but the different delta functions. These are the different delta functions located at different points. So these basis functions. So over here, for a 5-dimensional vector, let us go assume, let it be a 3-dimensional vector for simplicity. Say n is equal to 3, and this vector x is given by like x1, x2, x3, and the corresponding basis functions are something like that: 1 0 0, b2 0 1 0, b3 0 0 1. So basically, if I combine these different basis functions b1, b2, b3, they are nothing but the shifted delta function. So these are nothing but, so I can represent this as, they can represent it as delta n minus k, and set of that, set of delta n minus k for all k belonging to this particular set 0 1 2. Basically what? This is basically delta n delta n minus 1 and delta n minus 2. So accordingly, if I have infinite dimensional vector, so in that case, these basis functions are nothing but delta n minus k for all k ranging from minus to plus infinity. So that is the kind of connection that you can make with this vector space representation initially, with this vector space representation and the notion of signals that you have already studied before. Now coming back to the concept of the inner product. So let us now assume that, okay, we have got one particular signal xn, one particular signal xn, and I would like to find out the inner product. So let me write down the inner product between x of n and h of n. What is that? So that can be represented as, so when I write x of n, that means it's basically a vector over there, xn hn bar. And let us assume that these two vectors xn and hn, they are having infinite dimension. Both of them are ranging from minus to plus infinity. So basically this can be represented as summation x of k h of k star, where k is ranging from minus to plus infinity. Similarly, now referring to that particular concept, now if I try to find out the inner product between two signals which are having continuous variation. So as of now, we have considered the signals like a discrete signal. So x of n, x of n, y of n, h of n. That means we have started our discussion with the discrete kind of signals. Now try to visualize the same concept in the continuous form as well. So similarly, if I have two signals like x of t and h of t, so in that case, the inner product, you can also find out the inner product. And over here, the dimension is between x of t and h of t is given by x of t comma ht bar, that is the complex conjugate. Now here, instead of having a summation, you should have an integration over there, and that is given by x of t h star t, x of t h star t over there, and or you should write over there not t, you can also write like tau to make sense, because t here represents the time actually. So you can write like x of tau h tau d tau, where the range is from minus to plus infinity, something like that. That will give you the inner product between two particular signal xt and ht, which are continuous in nature. Now the thing is that, now let us move a bit further. Instead of considering one signal as a simple signal, let us now try to focus on a particular type of signal, which is all of us very much familiar with. Now let's assume that one signal that we are talking about, one signal is a sinusoidal signal, for example. So this x of t can be represented as a naught cos omega naught t plus phi naught. A sinusoidal signal or cosinusoidal signal which is having a frequency of capital omega naught and the initial phase of phi naught. Now, in electrical engineering, you'll find that this sinusoidal signal is having serious implications. So there are several reasons for that. First of all, in electrical voltage generation, for example, we are looking for a perfect sinusoidal signal. So in our household, we have a 50 hertz sinusoidal wave. So we'd like to generate this particular thing from the generator itself, which is rotating. So you have that particular thing rotates in the constant magnetic field, and that will give you this perfect sinusoidal wave, a sinusoidal wave having a frequency of 50 hertz in our country. In other country, it is also 60 hertz. That is one reason. Second thing is that if I consider our simplest electronic or electrical components like resistor or inductor or capacitor, then you see that if you provide this sinusoidal signal as your uh, input, as input voltage, in that case the current is also sinusoidal of the same frequency. That is another important observation. So, for example, if your input is say A naught cos omega naught t plus phi naught, that is the input voltage, then the current is simply, for a resistor, the current is simply the entire thing divided by R, the resistance value. So only the amplitude gets modified, but the frequency and the phase remains intact. Similarly, for the inductor and for the capacitor, the same logic is also applied. So therefore, so that is the smoothest function. This cos function or sinusoidal function is the smoothest function available in the universe. And if you derive this one, if you find out the derivative of this particular thing, you will see that always that will, if you integrate the cos, you'll be getting sine. If you integrate the sine, you'll be getting cos. Forget about the minus plus sign, because minus plus doesn't have any significance on the initial on the frequency of the signal, but it is always, and that will give you always a sinusoidal signal altogether, right? So sinusoidal signal, they are very much useful because of some reason. So what are those reasons? So first of all, that is the reason number one. If I write the naturally generated signal, naturally means in electrical power system, we are looking for a perfect sinusoid always. Second one is that the second reason behind behind the choice of this particular signal, A naught cos omega naught t plus phi naught, is that for basic electronic components, for basic electronic components, voltage current relationship is sinusoidal of same frequency if one of the, or rather if not exactly one, if the excitation is sinusoidal. If the excitation is sinusoidal, then you can expect, for example, for a voltage for a resistor, if you provide the voltage as a sinusoid, then the current will also be sinusoid of the same frequency. So I can consider that the sinusoidal signal is always closed under several operations, because for resistor it is basically the current voltage relationship is basically the division, the voltage, the current is given by the voltage divided by the resistor. However, for the capacitor and for the inductor, this is not a simple division. Rather, as you know, V is equal to, for an inductor, V is given by L di dt. For a capacitor, this is completely different. I is equal to C dV dt. So this is also the current voltage relationship. This is not linear, rather they follow the integration and the differentiation. So therefore, under these different operations like integration and differentiation, these sinusoidal signals, these are the closed. These signals are closed under this particular operation. And finally, if you just consider also the addition of two sinusoidal signal of same frequency, that will also give you the same frequency sinusoidal signal. Suppose I am having one signal x1t as a naught cos omega naught t plus phi naught, and the second signal as a1 cos omega naught t plus phi 1. Only the change lies in the amplitude and the change lies in the phase, but the frequency remains the same. And if I add these two signals, then also you will see that ultimately what you will be getting is basically another sinusoidal signal of having the same frequency, but the phase might be different. And finally, the most important thing is that is the smoothest function. Smoothest function available in the universe. That means what? That means no matter how many times you integrate, you differentiate, you'll be getting the same signal of same frequency. Same signal means the frequency remaining the same, only the amplitude and the phase might be different. So with this basic understanding about the vector space representation, I would like to stop here.